Welcome. We are looking at numerical solutions to the diffusion equation as well as analytical solutions, and the trick is always to reduce, if you are looking for analytical solution, the PDE to ODEs and solve them. And there are several ways in which you can turn them into ODEs. We saw variable separables, we saw the dimensional analysis based variable substitution, which reduces the equation to a ODE. So, now I want to talk about another way of reducing the PDE to ODE, which is based on what is known as Fourier transforms. Okay. So, the equation that we are trying to solve is the diffusion equation. And we are going to perform a Fourier transform on the variable c. Now, c is a function of both position and time. Okay. The line below x indicates that x is a vector, because the position is basically given by x, y, z, or x1, x2, x3. Okay. So, x is a vector and t is time. When we say Fourier transform, there are two Fourier transforms one can think of. One is what takes the time domain into frequency domain, which is a Fourier transform which is extensively used by electrical engineers. For example, when you are doing analysis of signals, you are generally trying to take what is there in the time domain and put it in the frequency domain, right. You can analyze voices, for example, using that kind of Fourier transform. But that is not the kind of Fourier transform in which we are interested. It is very natural in material science to look at this Fourier transform, because this Fourier transform takes from the space to the Fourier space. Sometimes it is also known as the reciprocal space. All the diffraction experiments, for example, take the information about the arrangement of atoms in a crystal from the real space to the reciprocal space. So that is equivalent to a Fourier transform too. So what we are talking about is a spatial Fourier transform. Okay. And in spatial Fourier transform, we go from x to k. So this is the wave vector space, okay, or the reciprocal space. So if we assume, so the Fourier transform is typically given C of k comma t is equal to integral minus infinity to plus infinity. You take C of x comma t, multiply by exponential I k dot x, and then you volume integrate over the x. Okay, so that is the Fourier transform. There are factors. Sometimes people use 1 by 2 pi, or sometimes people use 1 by root 2 pi. So there is some constant factor here. So let me just call it some a. We will not specify it, it is not very important for our purposes today. But if you do a Fourier transform, actually you need to look up the documentation of your Fourier transform to see what is the number that is used. There are many different ways in which this constant can be introduced. Some introduce it only in this way, which is known as the forward Fourier transform. You take the spatial domain information and you integrate out the spatial part, so it becomes just a function of wave vector. Some introduce it only in the reciprocal or in the reverse or inverse Fourier transform, where you take this and multiply by exponential minus I k dot x and then integrate it over dk. That is, you do this in the reciprocal space. So some do it in that fashion. So some do it symmetrically in both the forward and inverse Fourier transform by putting 1 by root 2 pi. So you need to look up, and generally sometimes people prefer 1 by root 2 pi in both, because that is symmetric and you do not have to remember which way the constant is kept. The other thing to remember is that sometimes Fourier transform is defined with exponential minus I k dot x, and inverse Fourier transform is defined with exponential I k dot x. So again, so this is a convention. You can define it whichever way you want, but you need to look up the documentation if you are going to use Fourier transform for your purposes to know what is the right definition. Okay. So let us say that this is the Fourier transform definition that we are going to use. Then using this we are going to reduce this equation to a ODE. So that is what we want to do. So how do we do that? Let us take the equation dou C by dou T is d del squared C by del x squared. Now I am going to replace C by its Fourier transform C of kt. I am not going to write this kt, xt, etc., but I am going to put a tilde. So C of k comma t I am going to call as C tilde. Okay. So dou by dou t of C tilde is equal to d del squared by del x squared acting on C tilde. Now what is this C tilde? We know that C tilde is nothing but integral C exponential I k dot x dx is equal to d del squared by del x squared acting on C exponential I k dot x dx, right. Now you can interchange these two operators, there is dou by dou t, there is integral. So I am going to take dou by dou t inside. If you take this operator, it will just pass through this entire thing, because nothing here is except for C, which is a function of t. So this integral, the entire integral will give C of k comma t, and that is the only time dependence. So the partial derivative in that case becomes an ordinary derivative. So you have d by dt of C tilde, right, because it is nothing that is happening there, is equal to, on the other hand, if you look at on this side, on the right hand side, we see that dou by dou x will act on this quantity, right, because these are like coefficients in the front. And so this is going to, one dou by dou x is going to get I k out, the other dou by dou x is going to get another I k out. So you will have I squared k squared, that is minus k squared when this acts, but after that it is going to leave the C exponential I k x dx the same. So that is going to be C tilde still. So you end up with this equation minus d k squared C tilde. As you can see, this is an ODE which can be solved, because it is ODE in d by dt. You just need one initial value to solve this equation, and so transforms, I mean using transforms like this to solve PDEs is a very common trick. Now in our case we are going to do this numerically now. I am not going to show you how to solve beyond this point analytically, but you can look up textbooks. For example, derivation of this itself is available in Kreyszig's book. Okay, so it is given as one of the solved problems using Fourier transforms to solve the diffusion equation. In his case, like I said, he talks about heat conduction equation. Okay, but it is the same, so you can solve this. Now let me say that if I have a numerical way of getting C tilde from C, right, then I will be able to solve this equation. For doing that, we need to know about what is known as fast Fourier transform. Okay. The fast Fourier transform algorithm, FFT as it is commonly known as, is one of the best known algorithms. It is one of the top algorithms of the last century, and it has transformed the way several experiments are done, fast Fourier based spectroscopic techniques for example. They are not possible unless you have a way of calculating Fourier transforms very fast, and the FFT algorithm gives a way of doing the Fourier transform very fast. But the Fourier transform that FFT does is basically a discrete Fourier transform. So it is sometimes called as DFT. It is discrete Fourier transform. What do we mean by that? See, when I want to solve the equation numerically, like I told you, I am going to take the system and I am going to split it into node points, and these node points is where I will have the value of the composition. So, C x comma t is nothing but a vector C, right, at any given time t. So, it will give me C at 0th position, C at 1 position, C at 2 position, etcetera, up to C n minus 1 position, or we sometimes write it as C 1 etcetera up to C n at time t, right. So, this is a set of discrete values, and you can do a Fourier transform on that, and you can get a set of discrete numbers in the Fourier space. Okay. So, that is what the Fourier transform does. Now, let us say that we do a Fourier transform. So, the equation that we want to solve is d c tilde by dt is equal to minus d k squared c tilde. Suppose I have given C and I can generate C tilde discretely at every node point. I have C in the spatial nodes, and I define C tilde in the reciprocal space again at certain reciprocal points. If I know that, this I can discretize. So, it is C tilde t plus delta t minus C tilde t divided by delta t is equal to minus d k squared C tilde, and I am going to take it at t plus delta t. Okay, you can also take it at t, but as you will see, t plus delta t is possible, because this is just see, this has just become a linear equation, just it is dk squared c, right. So, it is just algebraic. So, I can now take C tilde and then on this side t plus delta t, it is already there 1, and delta t multiplied and this minus, when it comes here it becomes plus d k squared delta t is equal to C tilde of t, right. I multiplied here, I brought this term here, I took C t there. So, if you know the initial configuration for composition at some time t equal to 0, if you know what C tilde is, C tilde at time t plus delta t is obtained just dividing by 1 plus d k squared delta t. So, it is a very simple implementation which will solve the diffusion equation. This technique is known as spectral technique, spectral because it uses the Fourier spectrum or Fourier transform, and in terms of accuracy this is the best that you can hope for. Okay. It depends on your discretization, how many k points you are going to take and integrate and things like that, and because it is implicit, because all the right hand side is at time t plus delta t. So, everything is at time t plus delta t. So, because of that there is no restriction on the delta t that you can take. Okay. So, here is a point at which point it is also better to say something about these issues. There is this problem which is known as stability. This is because on computers we do not represent numbers exactly, but they are only represented in an approximate manner. So, if you have this approximate manner representation, then there will be errors in your representation. These errors, if they interact with your algorithm or your method of doing calculation, and if they start growing, such a method is said to be unstable. The explicit method, which works very well because you can take very small, you can just write a direct algebraic expression and evolve the composition profile, has severe restrictions on the delta t that you can take for a given delta x. If you take delta t larger than that, then it runs into stability problems. The errors start growing and the system starts giving you nonsensical results. So, this is the problem of stability. Accuracy is different. Even in a problem which is stable, if you take a smaller and smaller delta t, you will get more and more accurate results. So, in the case of implicit method, where we take the right hand side in the future time, where it has to be solved by solving a matrix equation. So, it is costly in terms of solution, but it is favorable in terms of the larger delta t it allows you to take. In fact, you can take whatever delta t you want, the system will never become unstable. That is, the problems associated with accurately representing the number they do not interact with the method and grow the error. Okay. So these two are separated. So you might have some accuracy issues because numbers are not represented exactly on the computer. So when you do calculation, that error will be there, but it will never interact with the algorithm itself and give you wrong results. So implicit method is always preferred, and you can see that when you do a Fourier transform, you finally end up with a very simplified equation which can be implemented in an implicit fashion, which means you will get the solution fairly easily and straightforward, as I am going to implement and show you in the next part of this lecture. Thank you.